So, in the last video we have seen we have seen the properties of symmetric or skew symmetric matrices, and given a matrix A, if it's a skew symmetric matrix, we have seen certain properties. The same way, so if you are given a matrix, you can check A transpose bar equal to A. So, if you check that, if you verify that, then it is skew symmetric. So, that's what you do to check the matrix is skew symmetric. But for the differential equations, if it's a general differential equation, if it's a non-linear, it may not be, it's like a general matrix. So, if it's a linear equation of second order, I can always put it in the this form, that's a kind of Hermitian form or skew symmetric form. Okay, skew symmetric, self adjoint or symmetric depends on the coefficients. Okay, so we say that it's we will just show that it is Hermitian as an operator. So, any second order, we are only looking at the second order linear homogeneous equation. So, the operator for the matrix we are replacing with second order linear differential operator. So, which is almost Hermitian. So, we need to give certain boundary conditions to make it really Hermitian, that is what we are seeing. So, we will just we will do that today. So, we will just show that that operator is actually self adjoint or Hermitian. Okay. So, we will look into the equation again. So, you just consider this. So, this is the differential equation part. So, this is the differential equation, this is replacing, this is the operator A, instead of Ax you have My is here plus lambda some function of xy. So, that I want to put it in this form Ly equal to lambda y, where I want to make this L is self adjoint or Hermitian. So, what I did is in the last video we have seen that we calculated. So, we want to show, if you want to show that L is Hermitian, this is the definition we have seen. So, this dot product should be same for every function f and g. You take any functions f and g, this is what this should be satisfied. So, we have taken the left hand side, and we also have seen what is the dot product once you know what is the differential equation. So, once you know what is this L, which is this, okay. So, which is this, once you know what is L, we defined the dot product in this fashion. Okay. So, this is the dot product we have defined. With respect to this dot product, we want to check whether L is Hermitian or not. That means we want to verify whether this equality is true or not. So, we calculate the left hand side, so which is like this. If you, so we have seen that it is actually this. So, now next step is just use integration by parts, bring this L, this differential operator. So, integration by parts, basically what it does is simply take the derivatives onto the other functions. If you have a derivative of f into g as in the integration as an integrand, so by integration by parts what it does is basically takes the derivatives onto the other function. So, that is what we do now. Okay. So, is here, so you have so you can do the integration by parts. So, just by integration by parts what we get is integral, so you have px df by dx, so that is antiderivative into g bar of x. So, this you take limits a to b minus minus plus, and it is going to be a to b. What you have is px, and only first term I am doing. So, px df by dx into g bar of x dx. Okay. So, this is what you have after first integration, and the other one you write as it is, the other term, that is simply integral a to b qx fx into g of x bar dx. So, now what happens? So, this you cannot do any, so you do not know anything about f and g. So, leave it as it is, this one. So, this is minus px df by dx into g bar of x at a to b plus one more integration by parts here. So, if you do that, what you get is simply antiderivative of this is one function, and px into g bar of x is another function. So, you think of this px into g bar of x is another function, and df by dx is one function. So, if you do the integration by parts here, so you get fx and you have px px g bar of x sorry wait. So, when you do the integration by parts, what you get is df by dx, and you have you need to differentiate other part, that is actually giving d dx of px into g bar of x. This is what you have, the first integration by parts. Now, what you have is you do this is one function and this is another function. Okay, this is another function. So, if you do this, what you get is fx, and you have the derivative. So, d dx of px, just a minute, I think I made a mistake. This is what is px df by dx gf. Yeah, oh, I think this is a mistake. So, wait. So, actual thing is if you do the integration by parts, px dfx, so you have a px df by dx, and you have to differentiate this g bar. So, that will be g bar by dx, okay, g bar derivative. So, that is what is missing. So, this is what you have. So, this one, now you think of this is one function, other function is px into dg bar by dx. So, if you do that integration by parts, you have fx into px dg bar by dx. This you take the limits from a to b and you get a minus sign, and now you have an integration from a to b, and what you have is fx and the derivative of px into dg bar by dx. So, you have a d dx of px dg bar by dx. So, this is what you have. Okay. So, this into this minus this is as it is. So, you have qx fx g bar of x dx. So, this is what you have. So, this is equal to, so if you can put all these boundary terms, these are the boundary terms first two. So, this you can, px is common, px times, so what you have is fx dg bar by dx minus df by dx into g bar of x. So, this is what this, for this whole thing you take limits, x is from a b. So, this at b, this whole quantity at b minus whole quantity at a, and this two terms I can put it like that, and then what you have is now this you can put it together. So, this is from a to b, fx is common. So, I am combining this whole thing together. So, this will give me d dx of px dg bar by dx plus g bar of x, qx g bar of x, qx g bar of x. So, this is what you have for this function. So, what is this one? This is exactly, so what is this one? This is actually equal to px, and I will write f into g bar dash minus f dash g bar. Okay. So, from a to b with the limits. Okay. So, this is what you have, minus integral a to b fx into, what is this one? This is actually plus, and with the minus, if you want to put take this minus inside for the whole thing. Okay, minus and minus, and if you look at this one, this is exactly your LG. Okay. So, LG is, that is actually LG bar of x dx. Okay, that is not actually LG. So, you have to divide with 1 by omega x. Once you have a 1 by omega x, you have to multiply also. Okay. So, with 1 by, so you have this operator 1 by x, 1 by wx minus d dx of this whole thing up to here will give me this, and what you have is wx, that is a weight function dx. So, this is exactly, so this is nothing but px, this is fine. So, fg bar dash minus f dash g bar, this whole thing from a to b. Okay, x is from a to b. So, it just limits, plus this is nothing but f L g, because this L is actually a differential operator. So, differential equation with the real coefficients, those are those functions A1, A2, A3 all P, Q, R, PQ, right. You have P, Q, W, these are all real valued functions, they are also bar does not make them anything. So, LG bar is actually LG whole bar, okay. So, if you do put it, think of like that. So, this is LG bar, so that is same as LG bar actually, this is same as LG whole bar. So, that will give you this dot product. So, you see that second order, if you start with the second order equation, that is LHS is left hand side is LFG is actually the same as this one LFG. So, this dot product you want this to be this, okay, for a second order differential equation, linear second order differential equation. So, for that I have these boundary terms, unless I make them 0 I cannot make this second order differential equation as skew symmetric or Hermitian, okay. So, it will be Hermitian if I can remove these boundary terms, okay. So, for that what we do is we take this system, this equation, differential equation, and I define certain boundary conditions. So, I have A to B, this is a domain. So, we have only finite domain A at B, this is the boundary A and B, these points are boundary points. So, at these points you give the boundary conditions, so that I can make, so if what kind of boundary conditions that will make this quantity 0. So, let us start with the regular Sturm-Liouville system. So, if I do this regular Sturm-Liouville, so there are different cases, different boundary conditions will give you a different Sturm-Liouville problems, okay. So, let us see usual one, that is a regular Sturm-Liouville system, regular Sturm-Liouville problem, okay. So, problem. So, here what you have is you have this Ly equal to lambda y, okay. So, where L is minus 1 by Wx ddx of Px ddx, this is operator, okay, minus plus Qx. So, this is what is your L. So, if P is not 0, P never be 0, by the way, if what is P? P is actually equal to exponential of integral A1 by A. So, this will never be 0. So, you can see that this will never be 0 wherever x is there, x is in A, B open interval, okay. So, in the open interval P of x will never be 0. So, if P of x is non-zero for every x in the open interval, anyway it is non-zero. So, I include the points A, B, okay, then it is regular, then it is regular, okay. So, if you can write like this, where it is a regular Sturm-Liouville system if where P of A is non-zero and P of B is also non-zero, okay. So, in this case we say that this is a regular Sturm-Liouville system. Q, what is Q? Q is actually A2 by A0, right, A2 by A0 into Px. So, A2 can be, so it is a A2 of A2 by A0 that can take both positive and negative values. So, that means Qx can take both positive and negative, it can take any value, but P is always positive. W you want it to be positive, for the reason you will know. If it is not positive, why it has to be positive, okay. So, you will see the reasons. So, you see that Px is always positive, okay, x belongs to AB, and you do not know here a P of AB, okay. So, only in the open interval you know that it is non-zero, okay. And what happens PQ, Q can be anything, Q can be anything. So, I am not imposing anything, you see P is always positive, Q is this, Wx is also you need to be assumed that is positive, okay. So, need to be positive, this is you can assume that, we assume that W is always positive. Reason is, if it is negative, what happens to this dot product? If you look at the dot product which you defined, if W is negative, when you take the same function g equal to f, what you have is f square into Wx, the integral quantity. So, dot product you want it always to be positive quantity, okay. So but that is going to be negative if W is negative. So for that reason we can always assume that W is 0. So you, for your problem, so all the differential equations with when you take this right hand side, this third function with the parameter, so you always assume that A3 is always positive, okay. So it takes the positive values, A3 by A0 will always be positive function, okay, that is your W. So with this then you say that is a Sturm-Liouville, regular Sturm-Liouville problem if mainly Px is positive. So in this case the boundary conditions, you make this regular Sturm-Liouville problem, the boundary conditions are like this. You consider some alpha 1, y is the unknown function, so y at A plus alpha 2 y dash at A equal to 0. So this is the one boundary condition, okay. So these are the boundary conditions. What are the boundary conditions we have? This is one at A. So other one is, you call this some beta 1 y at B. So at B I am giving beta 1 beta 2 values and y at B equal to 0. If both alpha 1 and alpha 2 are 0, so there is no boundary condition. So at least one of them, not both of them are 0, okay. So not both alpha i's or beta i's are 0, okay. So you can say that this is not both the alpha i's, both the beta i's are 0, otherwise there is no boundary condition there. So these are the boundary conditions if you prescribe. What happens to this term? So now we always look at this, I want to make this, I give the boundary conditions, regular case these are the boundary conditions, because Px is non-zero at AB, so I have to make this quantity, okay. So this quantity I want to make it 0. So if f and g are two solutions of this system, okay, you take f and g are two solutions, okay. So if you have f and g are two solutions corresponding to some lambda, okay, what happens to that? So we will see with these boundary conditions, the moment you give these boundary conditions, now this equation Ly with these boundary conditions, let us write this regular Sturm-Liouville again. Ly is lambda y, and these are your alpha 1 y at A plus alpha 2 y dash at A equal to 0, and beta 1 y at B plus beta 2 y dash at B equal to 0. So this is the regular Sturm-Liouville system, so x in AB, and you have a P at A and P at B are non-zero. So this is the condition. So this is the regular Sturm-Liouville system. So once you have this, so I want to see any solutions of this system, this problem, any solutions if you put it here. So that is what, right, you take any solutions f and g and you take this operator L f g has to be f L g, any functions that are the solutions, part of the solutions of this equation, okay. So let us consider two solutions. Let y1 of x and y2 of x be two solutions, two different solutions rather, okay, two different solutions of the above system, of the system. System means a differential equation with the boundary condition. This is your system, okay, regular Sturm-Liouville system. So if you take that, so what you have is y1 satisfying this equation and these boundary conditions. So if you apply that boundary conditions, alpha 1 y1 at A plus alpha 2 y1 dash at A equal to 0, and similarly beta 1 y1 at B plus beta 2 y1 dash at B equal to 0. And similarly you have y2 is also satisfying y2 is also satisfying the equation Ly2 equal to lambda y2, okay, for some lambda, okay. So I am not saying that y1 and y2 are two solutions for the same lambda. So for some lambda these are the solutions, okay. For some parameter values of lambda, y1 is one solution but satisfying the same boundary conditions, y2 is also satisfying for some lambda this equation, but the same boundary conditions. So, if y2 is satisfying the same boundary conditions, you have y1 alpha 1 y2 at a plus alpha 2 y2 dash at a is 0. And similarly, beta 1 y2 at b plus beta 2 y2 dash at b equal to 0. Okay. Now you consider these two equations together. These two equations, if you take together, so you write it together. So consider these two or these two. Okay. So either these two or these first two solutions. So if you consider alpha 1 y1 at a plus alpha 2 y1 dash at a equal to 0. Similarly, alpha 1 y2 at a plus alpha 2 y2 dash at a equal to 0. If you consider these two equations, you get this one. So you know that we have already assumed in the boundary conditions that not both the alpha i's are 0. So that means for this is like a system y1a y1 dash a, okay, and y2a y2 dash a. This is the matrix and this is your unknowns alpha 1 alpha 2 equal to 0 0. So this is like you have system Ax equal to 0, and I know that alpha 1 alpha 2 is non-zero. Okay, alpha 1 alpha 2 as a vector, okay, is non-zero. So this is, we know this is the assumption we made, not both alpha 1 and alpha 2 are 0. Since this is non-zero, then the determinant has to be 0 because this is the homogeneous Ax equal to 0. When you have a non-zero solution, that means when you have a non-zero solution, determinant of A has to be 0. So that means the determinant, since this is this, you have y1 at a, y1 dash at a, and y2 at a, y2 dash at a. So this determinant has to be 0. We have this. So what is this determinant? This is nothing but y1 at a, y2 dash at a minus y1 dash at a, y2 at a. Okay. So this is equal to 0. So this is exactly what you have here. So P at a, say the lower limit P at a, that is anyway not 0, and what you have is f and g are two solutions of this system. Okay. If you take f is y1, g as y2, so what you have is, so this derivative, so you can see that this derivative, this is nothing but y2 is, if y2 is a solution, y2 bar is also a solution, okay, because it is a homogeneous equation. So lambda is always real, okay. So you can think of this, once you make this problem, alpha and alpha beta are real, okay, alpha i's and beta i's are real. So if you take y1 as one solution, y2 is also another solution, y2 bar is also a solution satisfying that corresponding to some lambda bar, okay. If y2 is a solution of this system, what you have is y2 bar is a solution of Ly2 bar equal to lambda bar some lambda, okay. If y2 is a solution for some lambda, y2 bar is a solution for the same lambda bar, okay, for the same, so conjugate of the same lambda. So with that, so its equation is anyway satisfied, and the boundary conditions we always assume that they are real. So because they are real, it satisfies same boundary conditions by y2 bar also. So you can think of y2 as y2 bar as well. So you can think of y1 and y2 be two solutions, okay, y1 and y2 bar be two solutions you can think. Then you have this one, you can make bars here, okay, because alpha 1 alpha 2 are real. So you do not have beta 1 beta 2 all real, so this you can put it as bars. So if you do that, so what you have is these are bars, so these are bars, so that exactly what you have in your form. So this is y2 bar. So this is exactly the lower limit of this special term, where P at a, when you put x equal to a, f and g are two solutions, f and g bar are two solutions. Here I have taken as y1 and y2, and the lower limit will be exactly will become 0, because this is 0. This implies P at a into y1 at a into y2 dash at a bar minus y1 dash at a y2 at a bar. This is 0. Okay. So, exactly do the same thing with these two other equations, do the same thing with the other equations, you consider them, put it as a system, since beta i's are different, beta i's both are non-zero. Okay. That means instead of alpha 1 alpha 2 you have beta 1 beta 2. So, you do the same thing, what you get is you have beta 1 y1 at b plus beta 2 y1 dash at b is 0. This is one equation. Other equation is y1 b y2 b bar plus beta 2 y2 dash b equal to 0. So, if you consider this, and you can see that since beta 1 beta 2 is not actually 0 0. So, what you have is a determinant of this matrix y1 b, y1 dash b, y2 b bar and y2 dash b bar. This determinant has to be 0. So, what is this determinant? This is, that is simply y1 at b into y2 dash at b bar minus y2 at b bar y1 dash at b. So, this has to be 0, you can multiply with pb, that is also 0. So, with this, these are simply lower and upper limits of this special term which you have. So, that makes it 0. So, if you consider this special regular Sturm-Liouville system with these boundary conditions, what you found is that special term Px and f and g are two solutions, any solutions of the system f g bar f g dash bar, right, f g dash bar minus g f dash bar, right, that is 0, f dash g bar, f g bar dash, okay. So, this is actually should write g bar dash and g bar f dash. So, that is g bar f dash, this term when you multiply, when you put these limits, it is 0, okay. For every f, for every solutions of, for every solutions, or rather for all solutions, for all solutions of solutions f and g of the regular Sturm-Liouville system, regular SL system, this is what I will write now onwards, okay, SL system. So, if you have as two solutions SL system for some lambda, lambda is a parameter, for some lambda if you take, what you get is that special term will become 0. So, this will simply gives you LFG is nothing but FLG, that makes it 0, okay. So, that makes it, this is true for every f and g solutions of this system. So, that makes it L is Hermitian. So, this implies L is Hermitian, Hermitian or self-adjoint, okay, you can also call self-adjoint or skew symmetric, and you are not in the finite dimensional, you are in the infinite dimensional space, okay. If you call it a space as Rn, there you have vectors are only, you have only n linearly independent vectors. Here you can have infinitely many linearly independent functions in the, as a functions. If you are in the function space, you linear independent vectors or functions, those vectors are, those functions are infinitely many, okay. Linearly independent functions are many, because 1x x square you consider, these are the solutions of, you can just think, okay, for some operator, for some lambda, these are the solutions. For these, if we give these kind of boundary conditions, they are all solutions that will make it, they form infinite dimensional space, okay. So, in this case, so you call this operator is self-adjoint, then we do not prove these properties in the infinite dimension, we just imitate. So, we just analogically we take these properties with for granted. So, what we have shown that the properties for the matrices when L is a matrix A, okay. So, what we have is, once you have this, you find, what is the next step is, find all the eigenvalues, find the eigenvalues and eigen functions, vector is actually here function. So, we call this Eigen Functions, that is what is the step. Okay. So, the next steps are like this. So, first step is this, find the eigenvalues and eigen functions. Second one is, and then so you can easily see that the property. So, different eigenvalues, distinct eigenvalues gives eigen functions. This is the property which we assume. Okay, eigen functions corresponding to distinct eigenvalues are orthogonal. Okay, with respect to the dot product that we defined for the operator L. What we have defined? This is exactly what we defined. So, if you have a differential equation with this operator, okay, so if you have this operator, so you have this inner product, you have with this dot product. Okay. So, with respect to this dot product, these functions are orthogonal. So, that is what you have. So, once you have, so your job is to find these eigenvalues and eigenfunctions, then you can say that these are all different eigenvalues. Different eigenvalues, if you take corresponding eigenfunctions, they are actually orthogonal. If they are not, suppose some eigenvalues are repeated, or for some eigenvalues are repeated, you may have two functions, okay, two eigenfunctions you may have, because the second order maximum you will have two linearly independent solutions. We know any second order equation you can have maximum two linearly independent solutions. So, fix your lambda, you may have two linearly independent solutions for that system, okay, with the boundary conditions. So, in such a case you may have maximum two linearly independent solutions for the corresponding eigenvalue. So, that means you have two eigenfunctions maximum, because it is the second order for an eigenvalue. So, if they are not orthogonal, obviously they for the same eigenvalue you have eigenfunctions. Eigenfunctions, if I call let us call this some V1x, okay, V2x are two eigenfunctions. If these are two eigenfunctions, you cannot expect because they are from the same eigenvalue, these are eigenfunctions corresponding to the same eigenvalue, they are linearly independent, that much is sure, because that is how you find these two. Okay. These are, you are simply going to solve the equation and with the boundary conditions by fixing this lambda. So, you are looking for non-zero solutions, these are the non-zero solutions, just like what you do for the matrix. For the matrix, how do you find the eigenvectors? You fix that lambda, you calculate all the solutions, non-zero solutions of that A minus lambda I x equal to 0. So, by doing that, if you look for non-zero solutions, they are eigenvectors. So, you are doing the same thing here, you fix this lambda in Ly equal to lambda y and the boundary conditions, you calculate the solutions, non-zero solutions. If you can get two solutions, okay, they are certainly linearly independent solutions, okay, two non-zero linearly independent solutions, and you cannot say they are orthogonal. Okay. What we did, if it is a repeated root, but that means I have two repeated x lambda, I have two eigen functions corresponding to this. So, in such a case you make them orthogonal by the Gram-Schmidt process, by redefining y2x as you can make them, okay, v2x into the process. So, this v1 of x plus, so you call this so something like v1, I want to, if you make orthogonal, I call this let us call this u1 and u2, and how do you make this Gram-Schmidt orthogonal process? I want to make them orthogonal like this, v1 is u1 of x. Similarly, v2 of x you take u1, that is actually v1, I defined v1 plus some constant times u2, these are known, u1 u2 are known. So, I choose my C in such a way that v1 v2 are orthogonal, this is the condition, v1 v2 with respect to that inner product is, that dot product is 0. Okay. So, with this condition, you put this condition, that makes it v1 v1 this dot product plus C times u2 into v1 has to be 0, this has to be 0. So, that makes it, that will give you minus v1 v1 by u2 v1. So, u1 v1 is known, right, u2 v1. What is the right hand side? v1 u2 v1. So, only u2 and v1 is nothing but u1, u2 are known. So, you can make it, you can, so put this c here and that is your v2. So, now v1 v2 are orthogonal, and v2 is nothing but linear combination of these functions u1 and u2. So, they are also linearly independent. So, you have two linearly independent solutions, but now they are orthogonal. So, something like if you have two vectors in the plane, you are given like this, you can make them orthogonal. Okay. So, by this is like u1 u2, you make them, actually you are taking u1 as v1. So, this itself is v1. Now, if you make orthogonal to this is your v2, that is what you did. Okay. So, I explained earlier. So, you can make them orthogonal if they are not, if you have two linearly independent eigen functions. Okay. So, what is the next step? What is the other properties which you have seen for the matrices which are skew symmetric, Hermitian matrices, eigenvalues and eigenvectors, and any vector in that space of functions, actually I can write in terms of these eigenvectors. Okay. And actually all these eigenvectors for the matrix you have, if it is n by n matrix, you have only, you will get n linearly independent eigenvectors. That is not true for the general matrix. Okay. If it is a Hermitian, you can always get n linearly independent eigenvectors. Okay. Some of them may not be orthogonal, so you can make them orthogonal by this Gram-Schmidt process. So, finally you get n linearly independent orthogonal eigenvectors. So, here also you get the same. So, all these functions you get, once you get all these eigen functions, and if they are not orthogonal, once you fix lambda, if you get two linearly independent solutions, you make them orthogonal by the Gram-Schmidt process. Finally, ultimately you get, for different lambda values you collect, all these form, all these are actually orthogonal functions. So, you have n linearly independent there for the space Rn in the finite dimension, here you have infinite, that is the meaning. Okay. So, once you have n linearly independent eigenvectors in Rn, any vector I can write in terms of them. So, here also any function, now any function, any reasonable function, okay, any reasonable function I can write in terms of these eigen functions, that is called complete. So, these functions, eigen functions form a complete set. Complete means any function I can write in terms of them, that is exactly our Fourier series. Okay. So, I will just write like that. So, eigen functions form complete orthogonal set. So, orthogonal we have already seen how to get them. It's complete means this means any function, let us say f I can write in terms of Cn, n is now from 1 to infinity, because you have infinitely many eigen functions, Cn un. So, let us call them, once I make them Vn's, I call them Vn of x. Okay. So, this is what you get, this is the actually Fourier series. What you see in the Fourier series, you get a different equation, you will get a different Fourier series. So, how do I find my Cn? Cn's I can easily find, you know the inner product which are orthogonal. So, you multiply Vn both sides with respect to this inner product, you make that integral as in the dot product. Okay. The dot product you defined as an integral, so that you make use of that dot product. So, if you do simply, if you have f is any function, you multiply Vn here and you multiply that weight function, you integrate both sides from a to b. If you do that, what you get is this dot product, which is, and you see that because Vn let us so you change the index, this is only from I is from R, you write it from m is from 1 to infinity, Cm Vm, this is going to be Vm, and you are making a dot product with Vn, and these are all orthogonal. If n is m is not equal to n, it will be 0. What is contributing here? Only Cn Vn. So, this will determine Cn. Cn is fx Vn by Vn. So, these are your Fourier coefficients. Okay. So, these are your Fourier coefficients, that is the Fourier transform. If you define, if you have a signal, time signal, you would first define Fourier transform as frequencies, different frequencies. This will give you those Fourier coefficients. Okay, so frequencies are 1, 2, 3, and so on. So these are okay. So you make frequencies. This is actually Fourier transform. Okay, different frequencies. These are Fourier coefficients, and you correspondingly you have this C and Vn is a Fourier. So any signal fx I can write in terms of frequencies. Different frequencies you break it. The signal you break it into different frequencies. So these are your frequencies you can define. Given a time signal, you can get this Fourier transform, and this is a kind of inverse transform. If you know, if you are given a signal here fx, you get a Fourier transform. That is a Fourier signal, Fourier transform, and using them you can get back. So if you are given like this, all these frequencies, you can get back your signal from this inverse transform. That's a Fourier series. Okay. So this is what you see from the Sturm-Liouville, any Sturm-Liouville problem, and so there you have a equation. So you have a differential equation. So given a differential equation with L, second order equation, for a different equation you have a different Fourier series. So you have kind of infinitely many Fourier series. Okay. For the infinite equations, you can create any equation, you can get such a Fourier series. Okay, that's what you will learn. Okay, so we will see this is what I have said. So if you have a second order equation with P of A and P of A, P of B is non-zero, and these are the boundary conditions makes that special term is 0, so that operator differential operator is Hermitian, so that you can conclude the properties using the properties of this Hermitian operator, okay, analogous to the Hermitian matrices. You can conclude that you can actually get any function you can write in terms of those Eigen functions. Okay. So these things are useful when you are solving certain PDEs, partial differential equations, in certain simple domains. Okay, by separation of variables method. When you are trying to solve the partial differential equations in some certain domains, what we do is we try to make the partial differential equation into an ordinary differential equation problem. So actually strictly speaking, you make it a Sturm-Liouville problem. You extract a Sturm-Liouville problem, and then you make use of this and finally solve the partial differential equation. That is where these Sturm-Liouville problems are useful. Okay. Also to create, so you can also see that different Fourier series you can get out of this Sturm-Liouville theory. Okay. So this is only case 1 which you have seen for the regular Sturm-Liouville system. So this is type 1. Like this you can get a different thing. So what else? How else? What is the next thing is? Next case is how do I give different boundary conditions when P of A is 0 or P of B is 0 or both are 0. Okay. Either P of A is 0 or P of B is 0 or both P of A and P of B are 0. In that case, what happens? Okay. If P of A, P of B is 0, so that is one system, that is or both are 0, that is called singular Sturm-Liouville system. Another case is P of A equal to P of B. Okay. In that case, what you see is you can look for some periodic Sturm-Liouville system. So we will see these two cases, how to make second order homogeneous equation. So that operator L as a Hermitian with the boundary conditions. So we will try to provide the boundary conditions in such cases. Okay, depending on what is P of A, P of B, how the P of A and P of B. Okay, if they are non-zero, it's a regular. If they are same, P of A equal to P of B, then you have a periodic system. If P of A equal to 0 or P of B equal to 0 or both of them are 0, that is one case, that is singular Sturm-Liouville system. So in that case, how to make this special term 0, so that the operator corresponding the actual differential operator L is Hermitian, so that properties of this operator can be used to get the Fourier series. Okay, that is what we will see. So we will see the next two cases in the next video, and then we will give different examples in each case. If it is a regular, so if you have an example for the regular system, so get the eigenvalues and eigenfunctions. So whatever we planned here. So all these 3 steps we will see, we take it and just conclude. Okay, so that's what we will do. So we will see this these next 2 cases, how to make the second order differential operator self adjoint or Hermitian. Okay, so thank you.